Imagine that one scientist measures a laboratory table in meters, another in feet, and a third in a local unit. Comparing the results would be difficult, and mistakes would be likely. Science needs a common measurement language. That language is the International System of Units, abbreviated SI. In this video, we will study the 7 base units, derived units, SI prefixes, unit conversion, and the basic rules for writing units correctly. A physical quantity has 2 parts, a numerical value, and a unit. For example, a length of 2 meters contains the number 2, and the unit meter. Without a standard system, the same length could be reported in meters, feet, inches, yards, or miles. A standard unit system lets measurements made in different places be compared directly. It reduces calculation errors, and helps other laboratories repeat and verify scientific results. A SI system is built from 2 categories of quantities. Base quantities are treated as independent quantities, and their units are called base units. Derived quantities are built from base quantities using mathematical relations. For example, speed is distance divided by time, so its unit combines meter and second. The SI has exactly 7 base quantities, and 7 corresponding base units. The first SI base quantity is length. Its SI base unit is the meter, written with the lowercase symbol m. Length describes the distance between 2 points. It appears in ordinary measurements, such as the height of a person, but also in scientific measurements, such as the wavelength of light, or the diameter of a planet. 1 meter equals 100 centimeters, and 1000 millimeters. The second base quantity is mass. Its SI base unit is the kilogram, written kg. Mass measures the amount of matter in an object, and also describes the object's resistance to acceleration. The kilogram is special, because its name already contains the prefix kilo. 1 kilogram equals 1000 grams. Mass should not be confused with weight. Mass is measured in kilograms, while weight is a force, and is measured in newtons. A third base quantity is time. Its SI base unit is the second, written with the lowercase symbol s. Time describes the duration of an event, or the interval between 2 events. In SI calculations, minutes and hours should usually be converted into seconds. 1 minute is 60 seconds, and 1 hour is 3600 seconds. The fourth base quantity is electric current. Its SI base unit is the ampere, written with the capital symbol A. Electric current describes the rate at which electric charge passes through a point in a circuit. It is measured using an ammeter, and is one of the fundamental quantities required to describe electrical and electronic systems. A fifth base quantity is thermodynamic temperature. Its SI base unit is the Kelvin, written with the capital symbol K. Unlike degrees Celsius, the Kelvin symbol is written without a degree sign. We write 300 K, not 300 degrees Kelvin. The Kelvin scale begins at absolute 0. The relation with the Celsius scale is T in Kelvin equals T in degrees Celsius plus 273.15. The sixth base quantity is the amount of substance. Its SI base unit is the mole, written mol. 1 mole contains exactly 6.022140076 times 10 to the power 23 specified elementary entities. These entities may be atoms, molecules, ions, electrons, or other particles. The mole is essential in chemistry, because atoms and molecules are too small to count one by one. The seventh base quantity is luminous intensity. Its SI base unit is the candela, written CD. Luminous intensity describes the amount of visible light emitted by a source in a particular direction. It is important in lighting technology, photography, display engineering, optical science, and applications where human visual response matters. Let us summarize the 7 C base units. Length is measured in meters. Mass is measured in kilograms. Time is measured in seconds. Electric current is measured in amperes. Thermodynamic temperature is measured in Kelvin. Amount of substance is measured in moles. Luminous intensity is measured in candela. These 7 units form the base of the entire C system. Most quantities used in physics are derived quantities. Their units are obtained by combining base units. Speed is distance divided by time, so its C unit is meter per second, written meter second to the power minus 1. Acceleration is the change in velocity divided by time, so its C unit is meter per second squared, written meter second to the power minus 2. Some derived units have special names. Force is measured in newtons. From Newton's second law, force equals mass times acceleration, so 1 Newton equals 1 kilogram meter per second squared. Energy is measured in joules. Power is measured in watts. Pressure is measured in pascals. Each of these special units can still be expressed completely in terms of C base units. Physical quantities may be extremely large or extremely small. Writing many zeros is inconvenient and can cause mistakes. C prefixes solve this problem by representing powers of 10. Kilo means 10 to the power 3. Milli means 10 to the power minus 3. Micro means 10 to the power minus 6. Nano means 10 to the power minus 9. The case of the symbol matters. Uppercase M means mega, while lowercase m means milli. Here are examples of prefix use. 1 kilometer equals 1000 meters. 1 millimeter equals 10 to the power minus 3 meter. 1 microsecond equals 10 to the power minus 6 second. Be careful with uppercase and lowercase symbols. 1 megawatt is 10 to the power 6 watts, while 1 milliwatt is 10 to the power minus 3 watts. They differ by a factor of 1 billion. Let us convert 72 kilometers per hour into meters per second. 1 kilometer equals 1000 meters, and 1 hour equals 3600 seconds. We multiply by 1000 meters per kilometer, and by 1 hour per 3600 seconds. The kilometer and hour units cancel. The remaining unit is meter per second. Numerically, 72 times 1000 divided by 3600 equals 20. Therefore, 72 kilometers per hour equals 20 meters per second. Correct C writing matters. First, leave a space between the numerical value and the unit symbol. Write 25 meters as 25 space m second. Unit symbols are not pluralized. Write 10 kg, not 10 kgs. Third, unit symbols are normally not followed by a full stop unless the symbol ends a sentence. Fourth, symbols named after scientists are capitalized, such as N for Newton, J for Joule, Pa for Pascal, and W for Watt. But the full unit names are written in lowercase. The International System of Units provides a universal and coherent language for measurement. It is based on 7 base units: meter, kilogram, second, ampere, Kelvin, mole, and candela. All other C units can be derived by combining these base units. Prefixes such as kilo, milli, micro, and nano allow very large and very small quantities to be written conveniently. Using C units correctly improves accuracy, prevents confusion, and allows scientific results to be communicated throughout the world. Thank you for watching.